All right, let's start the session on networked programming with one of our POPL distinguished papers this year. Andrew Hirsch is going to tell us about Pirouette higher order typed choreographies.
Yeah, thank you. Yeah, like Garrett said, I'm Andrew Hirsch. I'm a postdoc at the Max Planck Institute for Software Systems. I'm going to talk to you a bit today about higher order typed choreographies. And what choreographies offer is deadlock-free concurrent programming without session types. So let's start by thinking about an example. Alice wants to buy 2 books from Bob. To do so, she sends the title of the first book over to Bob, who looks up the price of the book and sends it back to Alice. They then do the same thing for the second book. Finally, Alice has to decide whether she's willing to pay for the books. She does so using the function f, which is a parameter of the protocol. She calls f on x and y, and then she sends the result over to Bob so that he knows whether she's buying the books. However, things can go wrong if Alice and Bob get out of sync. For instance, imagine that Bob decides that it would be more efficient to batch requests and look up the prices of both titles at once. So when Alice sends over the title Jane Eyre, Bob will wait for the second title before looking it up. However, Alice isn't going to send the second title until she gets a response for the first. Thus, Alice and Bob are in deadlock. We also have to think more about the function f that Alice uses to decide if she's willing to pay for the books. We already decided that f is a parameter of the protocol, but what can f actually do? Well, it could be very simple. Perhaps Alice just checks if x plus y is within her budget. But it could be more complicated as well. Maybe one of the books, say Ulysses, is actually for Kathy. So in f, Alice needs to send the price of Ulysses, y, to Kathy. Kathy then decides whether y is within her budget and sends that decision back to Alice, who calls it c. Alice then returns c and whether x is within her budget. Importantly, this means that f can itself contain communication. Since this lets us use basic code for Alice and Bob, reuse the basic code for Alice and Bob, whether or not Kathy is involved, this is actually a really important feature for real-world programmers. So, in order to support this, we want a way to write concurrent and distributed programs that guarantees deadlock freedom, can handle multiple parties, and is higher order, so that we can reuse functions even if we want to contain communication. Previous solutions have tried to offer solutions in this space, but none have quite fit the domain. For instance, multi-party session types can work here, but they're really hard to understand. And we need to write each program separately, increasing the probability that we get hard to debug type errors. Choreographies tried to fix this problem by allowing you to write every program together, but they lack any story for higher order programming, including functional programming. Thus, our solution is a choreographic lambda calculus called Pirouette. Pirouette's design is parameterized on a local language of messages, which allow computation with a single location. It lifts any type system for that local language to a type system for the entire language, and it has endpoint projections, which allow us to compile Pirouette programs to one program per location. In Pirouette, we refer to the threads of computation as locations, thinking of them as nodes in a distributed system. Pirouette programs manipulate local programs and values across all locations. So for instance, here, E is a local program running on Alice. Alice can evaluate that program to get a value V. Since values can be sent as messages, she can then send V as a message to Dave. Kathy might have some other program, E prime, which then evaluates to V prime. A choreography can return this value at the location Kathy. And we give the resulting choreography the type Kathy.t. We refer to types for choreographies as global types. So Alice can take a program she owns, like E, and evaluate it to V, and send that in a message to Bob. What Bob does is then bind that to a variable, in this case x. And we write that program with this squiggly arrow notation. This program says that L should evaluate E, send the result to L prime, who should bind that message to X, and then the entire network continues as C. Note that we're writing the send and receive together from a global point of view, rather than writing one program from Alice's point of view and another program from Bob's point of view. This is the magic sauce of choreographic programming that enforces deadlock freedom. We also allow Alice to decide what messages to send based on her local data. For instance, she might decide that if E evaluates to true, then she's going to send 3 to Bob. However, if it evaluates to false, she's going to send 5 to Kathy. We write this as an F expression where we branch on local data. However, there's a problem with this. If Alice hasn't sent a message to either Bob or to Kathy, they have no way of knowing whether they should wait for Alice to send them a message, or if Alice has taken the other branch. To fix this, we go back to the basic setup we've assumed so far. We had a new type of message, which we write L in square brackets. This represents Alice telling Dave that the left, or true branch, of an if expression was taken. Dually, we have an R message for the right branch. We write this again as a squiggly arrow. This says that L tells L prime that the true branch was taken, and then the entire system continues as C. With this in place, we can revisit Alice's decision. If E evaluates to true, Alice first sends L to Bob, so he knows whether to wait for another message. She then sends L to Kathy, so that she knows not to wait for another message. Finally, she can send that 3 to Bob. Note that Alice's E is interpreted in Alice's context. That means that when she evaluates E, it only refers to data that Alice owns. When she sends V over to Bob, he binds the result to X, which is only bound for him. But if Bob wants to send f of X to Alice, things are different. After all, we saw earlier that we want functions to contain communication. That is, f is not local. This tells us that we need 2 types of variables. Local variables reference data stored at a particular location. Each location has its own local context, telling us what local variables are available there. Global variables, on the other hand, contain data which is spread across the entire network. For instance, since f contains communication, it needs to be a global variable. In order to accommodate 2 types of variables, we use 2 types of functions. The first type binds a global variable. When we give it a type, we give it a normal function type, tau1 to tau2. Here, tau1 and tau2 are both global types. That is, they're the types of Pirouette programs. The second type of function binds a local variable at some particular location. We give it a special type, t at L to tau2. Here, t is a local type, or the type of a local expression, while L is a location. This tells us that the argument to this function will be evaluated at the location L before the function can be run. We've now seen all of the basic building blocks of Pirouette. I'm going to summarize Pirouette by comparing it to the simply typed lambda calculus. While lambda calculus starts with base types, in Pirouette we start with located types, where local types are parameter to the design of the language. Lambda calculus starts with base constants, whereas in Pirouette, we start with local expressions, where expressions are a parameter to the language. Pirouette also has communication primitives, which have no analogy in lambda calculus. There are 3 of them: send to value, send left, then send right. Lambda calculus then has functions and function types. In Pirouette, we have 2 types of function, global and local. Finally, it's common to add a Boolean type to the lambda calculus. Pirouette does this by assuming that Booleans are part of the local types. Similarly, lambda calculus usually adds Booleans true and false to its expressions, while Pirouette assumes that they are part of the local expressions. Finally, lambda calculus has if then else statements, which in Pirouette are located. So now let's move on to the semantics of Pirouette. Because Pirouette programs represent concurrent computation, execution can happen out of order. For example, if Alice wants to send E to Bob and Kathy wants to send E prime to Dave, they can execute their programs and send their messages in parallel. In order to represent this, we allow any interleaving of evaluations. For instance, Kathy may evaluate E prime to V prime, and then send V prime to Dave. Then Alice evaluates E to V and sends it to Bob as normal. When we look at the program text, though, something is kind of weird. We take a program which has Alice sending to Bob before Kathy sends E prime to Dave, and evaluate Kathy's program first, even though it comes after the send from Alice to Bob. Choreographies traditionally represent this using equivalences. So C is equivalent to C prime, where C prime is a possible reordering of C. For instance, if we consider again the program where Alice sends E to Bob, and then Kathy sends E prime to Dave, we can rearrange the program so that Kathy's send comes first. Note that we can do this because Alice, Bob, Kathy, and Dave are all disjoint, since otherwise a single locations program could be reordered. If C1 is equivalent to C1 prime, which then steps to C2 prime, which is equivalent to C2, then we can combine these together from C1 to C2. In other words, you're always allowed to rearrange programs during execution. However, there are some problems with this technique. First of all, inductive reasoning becomes now incredibly difficult, especially if you're actually working formally like we were. Second, it actually doesn't handle returns very well. To see this, consider a program where Alice sends E to Bob, and then we return the value of E prime on Kathy. Intuitively, Kathy and Alice are separate programs, so they can run their local programs concurrently. However, there's no reordering to allow Kathy to evaluate E prime before Alice evaluates E. We solved this by using a different representation of out-of-order execution. Let's consider evaluating this program again. In our representation, we need some additional information. First, we use a transition label. This tells us the type of step we're taking. In this case, it says that we're evaluating Kathy's program, E prime, to the value of E prime. Second, we need a set of B of blocked locations. These are locations which intuitively are already busy, and so they're not allowed to take part in any computation. We can take this step if we can evaluate this program without Alice sending to Bob. However, we have to add Alice and Bob to the set of blocked locations, since Alice and Bob are busy. After all, Alice is sending a message to Bob. We can take this step because E prime evaluates to V prime. But we also have to check that Kathy is not blocked. That is, we can only evaluate this if Kathy isn't already busy doing something else. This has some really nice properties. In particular, it easily handles returns, and it actually gives us a really nice induction principle, making Pirouette easy to formally reason about. While out-of-order execution tells us how Pirouette programs represent concurrency, they don't actually let us run them concurrently. We provide a translation called endpoint projection, which allows us to translate a Pirouette program to a single-threaded program for each location, which we can then run in parallel. For instance, the program alice.e gets translated to return E for Alice, while every other location returns nothing. If Alice sends E to Bob, then Alice's program sends E to Bob, while Bob's program receives X from Alice. Everyone else ignores this instruction. Note that because we match up the send and the receive together, we ensure that programs cannot deadlock. If Alice tells Bob that she took the left branch of an if expression, endpoint projection tells her to choose L for Bob. Bob, however, endpoint projection says that he should let Alice choose which branch he should take. But it only gives her one choice, the left branch. We'll see in a moment how Bob can offer Alice more choices. If we branch on Alice's expression E, then it's easy to project this for Alice. We just use an if expression. For everybody else, however, it's not clear what they should do because it depends on Alice's local data. So we use a trick which is called merging. And what merging does is it allows a location to offer more than one choice to another location. So if on one side they offer the left branch, while on the other side they offer the right branch, merging allows them to offer both branches. However, this is a partial operation, since not all programs offer a branch. This makes the entirety of endpoint projection partial. Furthermore, it introduces an ordering that we refer to as the less non-determinism ordering. With this in hand, we know how to project certain types of if statement. If Alice tells the other locations to take the left branch in C1, but the right branch in C2, then when we merge all of the other programs' locations, all the other locations' programs, excuse me, they take the branch that Alice tells them to. We validate our design through 5 important theorems. First, we prove standard type soundness, progress, and preservation. This tells us that well-typed programs don't go wrong. Second, we show that equivalence preserves types. This tells us that our type system plays well with concurrency. Third, we study the relationship between the traditional equivalence-based representation of out-of-order execution and our block set-based representation. We show that the equivalence-based representation is weaker, as we expected. Finally, we show the soundness, or not finally, excuse me. Next, we show the soundness and completeness of endpoint projection. Note that the less non-determinism order that shows up due to merging actually makes this really complicated to both state and prove. Finally, we show that Pirouette programs are deadlock-free by construction. And the nice thing about this is that this isn't complicated to state or prove. In fact, the proof is very simple, based on type soundness and the soundness and completeness of endpoint projection. Finally, all of these theorems are proven in talk. So, in conclusion, I told you about Pirouette, a choreographic lambda calculus, which is parameterized on a local language of messages, features out-of-order execution, and endpoint projections, which allows us to recover a program for every node. And these feature soundness and completeness theorems. Pirouette's also deadlock-free by construction, and everything's proven in Coq with a modular design. So you can instantiate Pirouette with your own local language today. Thank you. I'm happy to take any questions now.
All right. Are there any questions locally? Bunch.
Hey, super cool talk. Really love that. Thanks, Andrew. My name is Josh.
Thanks.
And this is maybe a small question, but just one thing I had is, do you provide interoperability between possibly different local type systems within this model?
No, we don't at the moment. Everything has the same type system, the same local language.
Have you thought about that at all?
Yes, but not in any technical way.
Yeah, really interesting stuff. Just curious if you have put thought into models for Pirouette, either in terms of embeddings in process calculi or sort of categorical style semantics?
I've thought about categorical style semantics, but not in any, again, not to any completion. In terms of embeddings into process calculi, endpoint projection kind of is that. So.
Hi, thanks for the talk. Is the set of locations, does it have to be known at compile time, or can it be open and you can...
It's known at compile time,
Okay.
but it can be any arbitrary set. We don't demand any extra structure.
Okay, but you have to know how many people are participating. Okay, thanks.
All right, we might have time for one online question. The question is, can you compare Pirouette with Murphy et al.'s ML5?
Yeah, so ML5 is a really interesting language, functional language for doing concurrent programming based on modal logic. So Pirouette is also somewhat based on modal logic, although I didn't get into that in the talk. But while Pirouette is based on the proof theory of modal logic, ML5 is based on the models of modal logic. So there's a bit of a difference there.
All right, and I guess I'll throw one question in. Does your transmittable values include functions? And in that case, how do you handle capturing global versus local variables and closures?
So you can only transmit local values, but if your local language has functions, you can transmit those just fine.
All right. Let's thank Andrew again.